Change one number about this wing, and a computer has to recompute the entire airflow from scratch. Do it 1,000 times to design anything, and you wait, and you pay. Unless you could learn the solver itself. One machine, built once, that answers any of them instantly. That machine is a neural operator. Welcome to ThirdEye Labs, where we make the unseen seen. Today, neural operators. Here is the pain, made concrete. Tilt the wing by a few degrees, the angle alpha, and the airflow must be solved all over again from nothing. Change the speed of the air instead, the Reynolds number, and again it starts from nothing. The spinner ticks a little longer this time. Design a real wing and you do not ask one question. You ask thousands. Each tilt, each speed, a brand new solve. Most are still spinning. The clock races, the bill climbs, unless you could learn the solver itself. One object, built once, that answers all of them at once, instantly. The spinners freeze, and every tile fills in a blink. Here is every network you already know. A fixed list of numbers in, a fixed list out. 3 values say, give it one extra number it never planned for, and it breaks. Its input shape is frozen at birth. But the things physics cares about are not short lists. They are whole fields, a temperature all along a rod, and a field has a value at every point. Between any two, infinitely more. So we need a machine that swallows a whole function and returns a whole function. That is an operator. We draw it as a portal, G, mapping one function space to another. Feed it any field and it returns the matching field. A smooth wave, a bump, a jagged step. Same portal, different question every single time. Concrete version. A metal rod heated in some pattern at time 0. That pattern is our input. Now let time run. Heat crawls from hot to cold, and the jagged start relaxes into a smooth final shape. That final field is the answer. The rule from any start to its final state is the solution operator. The portal is that rule. The classical road chops the field into a grid of endpoints, builds a giant linear system, and grinds it down, one instance at a time. The operator road skips all of it. Field in, field out, one step, and they match almost. Watch that thin red sliver. It is the price of approximation, and we keep it honest. Open the portal. One input point does not affect just one output point. It spreads its influence across the whole output by amounts given by a weighting we call the kernel. Sweep across every input point, let each spread its influence, and add them all. That running sum builds the entire output. That sum is the kernel integral. Between the two lines, the full kernel rises as a surface, a height over every pair of points x and y. The kernel is one single object, and every influence fan you watched was simply one slice of it. Hold the source point fixed, cut straight through, and the profile you expose is exactly that fan. The fan was the kernel all along. For a few classic, linear problems, physics even hands this surface to us by name, the Green's function. But for the real, nonlinear equations, no formula exists. So we stop writing the kernel down and we learn it. Let a neural network become the kernel and fit its shape from data. That single idea is the whole field. Learning the kernel works, but count the cost. Every input point talking to every output point. On a fine grid, that number is brutal. Here is the escape. Any field is a sum of pure waves, a few slow ripples plus finer and finer ones. The bars are how much of each. And in wave world, the kernel's whole job becomes one knob per frequency. Turn each wave up or down. The cost collapses. This is why the Fourier neural operator is fast. The full move is a round trip. Carry the field into wave world with the fast Fourier transform, turn the knobs, carry it home with the inverse. One repeatable layer. One honest catch. We keep only the low knobs and slide a frosted panel over the rest. The answer is near perfect, except at the sharpest edges where fine detail blurs. Mark that. First family. Sample the input at a fixed set of sensors. Push those readings through a network. Out come a handful of numbers, the recipe. Call them amounts of paint. A second network learns a fixed set of basic shapes, the same for every problem. The ingredients, now mix. Each amount of paint scales its matching shape, and they all add up to the answer. Ingredients times a recipe, and here is the magic. The answer is now a formula in Y. So ask for the value at any point you like. The output never needed a grid at all. That is DeepONet. Second family, using the wave trick. First, lift the single field into many parallel copies, called channels, for more room to think. Inside each layer, every channel takes the round trip into wave world, turns the learned knobs R, and comes back. But waves alone smear sharp features, so a second path keeps the local detail. The two braid together, and a rectifier folds away the negatives. That is one Fourier layer, stacked 4 deep. And the showpiece, train on a coarse grid. Then, without touching a single weight, feed a far finer grid, and out comes a far finer answer. Like a vector graphic, it has no fixed resolution. One honest catch: the fast Fourier transform demands an even grid. Hand it a bent, irregular shape and it refuses until you warp that shape onto a square first. Fix known, work ongoing. The first two families love a tidy grid. A turbine blade is not tidy. So, third family. Scatter points on the real geometry, connect neighbors, and put the field on the points. Each point sends a message to its neighbors, weighted by how far apart they are. And those weights are exactly the kernel from before, now sampled along the edges. Run it everywhere at once a few times, and influence spreads across the whole shape. Same integral, just on a graph. And the same set of learned weights runs on a totally different shape, with a totally different mesh. Learn once, run on any geometry. Discretization invariance, graph addition. One last problem. On a dense mesh, every point talking to every point chokes again. Edge spaghetti. The fix borrows a centuries-old trick from physics. Group far-away points into clusters and talk to the cluster, not its members. Long-range cheap, short-range sharp. 3 machines, mixing ingredients, turning knobs, passing messages, they look nothing alike. But strip them down and the same 2 parts fall out of all 3. A piece that mixes globally, across the whole field, and a piece that touches each point locally. Add a global mix to a local touch, bend with a nonlinearity. That one line is every neural operator. Stack the layers, and the portal is complete. A portal is born knowing nothing. And the irony, we teach it with examples from the very slow solver we want to replace. Run thousands of times, offline. Show it an input it guesses. We measure the red gap to truth, and push that error backward to nudge every part. The ordinary training loop, lifted to functions. Repeat it, run after run. The blue guess locks onto the orange truth, and the loss curve falls. A sliver of red always remains, honestly. But that needs a mountain of data. So add a second teacher, check whether the output obeys the equation itself. That barely needs data. 10 examples can do the work of 1,000. 100 questions. The classical solver is a truck that stops and grinds at everyone. A physics-trained network is quicker, but rebuilds for almost every new question. The operator pays a steep price up front, the training, and falls behind early. But once built, it clears all 100 in one blur. On the 1,000th question, it is not close. As the grid refines, the naive all-pairs cost explodes quadratically, while the Fourier route climbs almost in a straight line. One honest asterisk, making the training data is itself expensive. The speed is real. It is not free. 4 contenders: the classical truck, the physics car, the operator train, and the ordinary image network locked to one input size, a new mesh or a new parameter. The operator just answers instantly, where the others resolve, rebuild, or simply cannot. But here is the honesty. With almost no data, the operator wobbles until physics steadies it. And refine the classical solver forever, and its accuracy keeps improving, while the operator's aim is fixed by its training. Fast and flexible, not the most accurate. A model trained on calm flows has never seen a hurricane. Push it past the world it learned, and its confidence stays high while its answer quietly goes wrong. The wise move is to feel the edge and stop. Hazard 2, the one we flagged. Smooth physics the operator nails, but a sharp shock, a true jump it rounds off. The gold fit cannot match the cliff. Multi-scale designs are sharpening this. It is not solved. Hazard 3, mixing the data teacher and the physics teacher is a delicate balance, and training can shake itself apart. And Hazard 4, the theory is half-built. We can prove these operators can represent the solution. How much data they need, and when they converge, those girders are still being drawn. Which is exactly why this is alive. Attention, reimagined as a kernel. Operators that report their own uncertainty. And hybrids, where the old solver and the new one push each other forward. We started with one wing and a machine that choked on every small change. We end with one learned machine answering the whole family at once. Weather, heat, waves, flow through rock. A network that maps functions to functions, built from a global mix and a local touch. Taught by data and by physics, we did not just describe the portal, we built it. Find the rest of the math at ThirdEye Labs. If this clicked, the Fourier neural operator deep dive builds the fastest one of these, gear by gear, from a real paper. Thanks for watching and keep exploring. Next time, the network that learned physics. Please like and subscribe ThirdEye Labs if you enjoyed this video and let me know in the comments.